So let's start the new lesson for today. Today is our second lesson, and this lesson is about the transformations of the general power function. First of all, let's have a look at today's learning goals. So after this lesson, you will be able to determine if a function is a general power function or can be obtained by transforming a general power function. Second, you should be able to know how to apply transformations from the function y equals x to the power of n to the functions y equals a times k times the difference of x and d, and then raised to the power of n plus a coefficient c. And more generally, from any given function y equals fx to a new function y equals a times the function of k times difference between x and d, and then plus a coefficient c. Last, you should be able to sketch the graphs of the functions with the form y equals a times k times the difference between x and d raised to n power plus the coefficient c, and analyze their key features, including domain, range, parity, monotonicity, and behavior, and asymptote, etc. Okay, so today's lesson is broken into the following two parts. First, let's have a look at transformations of a general power function. Next, we're going to look at the transformations of any given function. All right, so we're going to talk about the following 5 transformations for a given general power function. First, we're going to see if we put a factor here in front of the whole function, what will happen? So what can we get from the original function to the function with a new coefficient a here? Next, we're going to see if we put a coefficient before the x here, what will happen? And next, we're going to see if we put a coefficient c here, the original function becomes the original function plus c, what will happen? And next, we're going to see if we put the minus d here, what will happen to the original function? And last, this transformation here is just a combination of the previous 4 transformations. So we're going to see how we can do this all together. Okay. All right. First, let's have a look at the first transformation. That is to multiply a coefficient a, which is not 0, in front of the original equation, y equals x to the power of n. Okay. I have set up some examples here to help you understand. All right, so let's consider the original function here. The original function is y equals x to the power of 2. And then suppose we multiply a factor of 2 here. So let's consider these 2 functions first. What will happen? So for the same x, I sampled 1, 2, 3, 4, 5, 6, 7. Okay, I sampled 7 points in the original function. So when x is minus 3, y equals 9, right? This is apparent. So when x is minus 2, y is 4. When x is minus 1, y is 1. When x is 0, y is 1. When x is 1, y is 1. When x is 2, y is 4. When x is 3, y is 9, right? This is a sample points from the original function. So if we put a new factor 2 in front of the whole function, so what will happen? for the same x in the original function, this new function here, the value of the function is enlarged by this factor, right? So as you can see here, when x is minus 3, the value of the new function is just twice of the original value, right? So we get 18 here. And when x is minus 2, the original function is 4, and the new function is twice of the original value, which is 8, right? And when x is minus 1, again, the original function is 1, and the new function is twice of the original value, right? So this also applies to the rest of the sample points here. So this means the original function, based on the original function, if we put a factor in front of the whole function, this is equivalent to stretching the original function by a factor of 2, right? So if we put a coefficient here, the parameter a corresponds to a vertical stretch or a compression, right? It depends on the value of a. If the absolute value is greater than or equal to 1, this is a vertical stretch, right? And if the absolute value is between 0 and 1, it should be a compression, right? Why? Because, okay, let's consider another transformation. So this time, let's consider the original function here with the transformed function here. Okay, let's see this transformation. So if you put a factor of a here, this time a is 1/2, right? So for any given x, in order, okay, for any given x here.
帮我拿一下，要人一份帮我拿一下。
Okay, for any given x here, you can see that the value of the function is compressed by a factor of 1/2, right? Because we just multiplied a factor of 1/2. Can you see this? So in a summary, if we put a parameter a here, this means we have a vertical stretch or compression by a factor of a. And if a is below 0, we also need to apply a reflection in the x-axis. Why? Okay, we'll use this example to illustrate. Okay, so this time let's consider this is the original function, right? So this time let's consider this transformation. How about we're putting a -1 in front of the function? If we put a -1 in front of the function, as you can see here, when x is -3, original value is 9. And if you put a -1, the function value becomes -9, right? This means for any x unchanged, the value of the function changes to the opposite, right? So if the original function looks like this, the transformed function should look like this, right? Which is a reflection in the x-axis. Understand? Okay, now let's have a look at the graphs on the right-hand side. This is in coordinates with the transformation table with the list of the points on the left-hand side, right? So this is our original, suppose this is our original function. And if we multiply a factor of 2, this function is stretched vertically by a factor of 2, right? And if we multiply 1/2 in front of the whole function, this function becomes here, which is a vertical compression by a factor of 1/2, right? Okay, next, if we put a -1 in front of the whole function, function is transformed here, which is a reflection in the x-axis, right? And if we put a factor of -2, if we put a factor of -2 in front of the original function, this means first we need to stretch the function by a factor of 2, right? And then reflect the graph in the x-axis, which is transformed here, right? And if we put a factor of -1/2, this means first we need to compress this function by a factor of 1/2. So this function becomes this one here, right? And then reflect the graph in the x-axis, so its function is moved here, right? Do you understand? Okay, so let's make summary. If the original function is y equals x to the power of n, and if we put a new parameter a here, this is equivalent to vertically stretch or compress the function by a factor of a. And if a is negative, a reflection in the x-axis. Understand? Okay, let's do a practice. How do you obtain the graph of y equals 3 times x squared from the graph of the function y equals x squared? Okay, I'll give you 2 minutes to think about this question. All right, have you finished? So how are you gonna obtain the graph of the new function from the original function? So the new function is just the original function multiplied by a factor of 3 here, right? So if we multiply a factor here, that means we have vertically stretched or compressed, right? As 3 is above 1, the absolute value of 3 is greater than 1, right? So this new function is obtained from the original function by stretching, right? Stretching the graph of y equals x squared by a factor of 3, right? Can you see that? Okay, so if we illustrate this in the graph, this is our original function, right? And if we multiply a factor of 3 here, the new function should look like this. This is our new function, right? And imagine that if you vertically stretch the graph of y equals x squared, function will become thinner and taller, and it will be transformed here, right? Okay, any questions? No? Okay, let's do another practice. How do you obtain the graph of y equals minus 1/3 of x squared from the graph of the function y equals x squared? This is the original function, and the new function is minus 1/3 times the original function. Okay, again, I'll give you 2 minutes to think about this problem. Okay, have you finished? So how do you obtain the graph of y equals -1/3 of x squared from the graph of the function y equals x squared? So note that the new function is the original function times a factor of -1/3, right? So this factor here corresponds a compression or a stretch, right? Because the absolute value is less than 1, so it should be a compression, right? And note that there is a minus sign. That means after the compression, we need to reflect the graph in the x-axis, right? So the solution is to vertically compress the graph of the original function y equals x squared by a factor of 1/3 and then reflect it in the x-axis, right? Okay, if we illustrate this in the Cartesian plane, we can see that this is the original function, right? So in order to get the new function, the new graph of the graph of the new function, first we compress the original function and it becomes here, right? The graph becomes the dotted line, dotted curve here. And then because we have a minus sign here, that means we also need to do a reflection over the axis, and then the curve comes here. This is the graph of the function y equals -1/3 of x squared. Understand? Okay, do you have any questions regarding the first type of transformation from y equals x to the power of n to y equals a times x to the power of n? No questions? All right, let's see the second type of transformation. That is, if we multiply a factor of k to x itself, so that means the original function y equals x to the nth becomes, first we times at k to x and then raise the whole multiple here to a factor to the power of n. So what will the new graph look like? So note here k is not 0. Also, let's consider a function here. This is our original function, which is y equals x cubed, right? So for example, let's consider the first transformation here. If we put a factor of 2 with x itself inside a square, what will happen? Okay, again, let's sample some points from the original function. For example, when y is -216, x in the original function is -6, right? And when y is -64, x in the original function is -4. And when y is -8 in the original function, that corresponds x equals -2, right? And etc. until y, if y is 216, x should be a 6 in the original function, right? So suppose we just keep y unchanged. If we put a new factor of 2 here, in order to keep the y unchanged, x should be 1/2 of the original value, which is -6, right? Only in this way, the 1/2 can be canceled with the new factor 2 here in order to keep the function x value in the function. In order to keep the value of the function unchanged, right? So, for example, if the y value is -216, if the original value is -6, the new value of x in the new function must be 1/2 of the original value -6, which is -3, right? Can you follow me? Okay, so following the same logic, if the y value is -64 and the original value of x is -4, the new value in the new function, which is enlarged by a factor of 2, in order to keep the y unchanged, the x in the new function must be 1/2 of the original value of x, right? Which is -2. So following the same logic, each value here is just 1/2 of the original value, right? So that is equivalent to we have compressed the original function by a factor of 1/2, right? Which is the reciprocal of this factor. Understand? So the conclusion is based on the graph of y equals x raised to the power of n, the parameter k corresponds to a horizontal stretch or compression. Whether it is a stretch or compression depends on the value of the k, right? If the absolute value of k is greater than or equal to 1, this corresponds to a compression, which is a little different with what we have learned in the previous conclusion, right? Because this time we multiply the k to x, not to the function k, not to the function y. So when the absolute value of k is greater than or equal to 1, this corresponds to a compression. Whereas when the absolute value of k falls between 0 and 1, it corresponds to a horizontal stretch. Understand? And if k is negative, it is a reflection in the y-axis. Okay, so let's have a look at another example. So suppose, again, this is the original function, right? So this time, let's have a look at another transformation. If we put a factor of 1/2 in front of x, what will happen? So for the same value of y, in order to keep the function value unchanged, note that if you put a factor of 1/2 here, you need to cancel the 1/2 here, right? So the x in the new function becomes twice of the value in the original function, right? So this is equivalent to horizontally stretch the function to by a factor of 2, right? Which is the reciprocal of this value here. Understand? Can you follow me? All right, so next, another example. Original function is here. And how about this time we put a -1 in front of x? Again, in order to keep the function value unchanged, we need to cancel the factor of -1 here, right? Which we need to, in which the x value in the original function becomes the opposite value of x here, right? So that is equivalent to we times a -1 to the original x in the original function, which is equivalent to we just reflect the graph over in the y-axis. Understand? Okay, so now let's have a look at the graph on the right-hand side. This is our original function, x cubed, right? And let's consider this transformation here. If we put a factor of 2, as we have discussed, in order to keep the function unchanged, how about here, in order to keep it on the same level of y, the x needs to be 1/2 of the original value, right? Which is equivalent to a horizontal compression by a factor of 1/2. Understand? So in this way, the function becomes here. Okay, and if we put a factor of 1/2 in front of the x here, in order to keep the y unchanged for each x value, the x must be twice of the value in the original function, which becomes a green curve here, right? This is the new function, 1/2 of x as a whole raised to a power of 3, right? Which is equivalent to a horizontal stretch. Understand? Okay, if for any of the 3 functions here, if we put a minus sign here, again, in order to keep the y unchanged for each x value, the x value should be the opposite value in the original curve. That means we need to do a reflection in the x-axis, right? So the blue solid line here becomes a blue dotted line here, and the red solid line here becomes the red dotted line here, and the green solid curve here becomes the green dotted curve here. Understand? Okay, any questions? No? Okay, let's do some practices. How do you obtain the graph of y equals minus 2x as a whole raised to the power of 3 from the graph of the function y equals x to the power of 3? Okay, I'll give you 2 minutes to think about this question. Okay, have we finished? So how do we do the transformation? So note here, we put a factor of -2 in front of x, right? So that corresponds to a horizontal transformation. Actually, a horizontal stretch or compression, right? So how do you analyze this? We can analyze it like this. If in order to keep the y unchanged for every value of x in the original function, we need to put a 1/2 in front of the x in order to keep the function unchanged, right? So actually, because there is a minus sign here, we need also to put a minus sign, right? So that means first we need to compress the function horizontally by a factor of 1/2, right? And then reflect by a factor of reflect the graph in the y-axis, right? Okay, so the solution is, in order to get the new function, we need to horizontally compress the graph of y equals x cubed by a factor of 1/2, and then reflect it in the y-axis. Understand? And if we draw a graph illustrating this, this is our original function, x cubed, right? So first of all, we need to compress it horizontally, which we get the function here, right? This is function 2x to the power of 3. And then remember there is a negative sign. So that means we need to reflect the dotted graph in the y-axis. And the curve here is the curve we want, which is -2x to the power of 3, right? Okay, any questions? No? Okay, let's see the next type of transformation. So this time we just add a factor of c at the back of the original function. So what will happen? This actually is the simplest case, right? So let's consider a function, for example, y equals x squared. And this time, for example, we put a factor of 1 at the back of the original function. What will happen? So when x ranges from -3 to 3, the original function is 9410149, right? And if we put the factor of 1 at the back of the original function, the new function is just 1 unit larger than the original function, right? So that means for each x in the original function, the value of the new function is 1 unit higher than the original function, right? Which is equivalent to translating the original function 1 unit up. Understand? As you can see here, by 1 unit up, the original function moves to the new function, right? Okay, any questions? And for another example, suppose the original function is y equals x squared. This time, the c here is a negative number. What does this mean? This means for any x values in the original function, the value of the new function is just 1 unit lower than the original function, which is equivalent to moving the original function 1 unit down, right? So in conclusion, based on the graph of y equals x to the power of n, the parameter c here corresponds to a vertical translation up if c is a positive value, or down if c is a negative value, right? Okay, so if we illustrate this by a graph, as you can see here, the red curve corresponds to the original function y equals x to the power of 2. And if we add a 1 at the back of the original function, as you can see here, this corresponds to a vertical translation up by just 1 unit, right? And if we put a -1 at the back of the original function, this corresponds to a vertical translation down by 1 unit, which becomes x squared minus 1, right? Okay, any questions? No? All right, let's do a practice. So how do you obtain the graph of y equals x to the power of -1 plus 1 from the graph of function y equals x to the power of -1? Okay, I'll give you 2 minutes to think about this question. All right, have we finished? So how do we obtain the new graph from the graph of the original function? So as you can see here, we add a factor of 1 to the original function, right? So that means we need to translate the original function up by 1 unit, right? So the solution is simply easy. To vertically translate the graph of y equals x to -1 up by 1 unit, right? Okay, so if we draw a graph to illustrate this problem, the original function is here, and after translation by 1 unit up, the new function becomes here, right? So note, accordingly, the horizontal asymptote also moves from y equals 0 to y equals 1. The vertical asymptote x equals 0 does not change because there is no horizontal translation, right? All right, any questions? No? Okay, if you don't have any questions, let's have a look at the fourth transformation. So this time, we subtract a factor of d to the x in the original function. So what will change in the graph? Again, let's consider an example. Suppose the original function is y equals x squared. Okay, so let's sample some points to check what change is there. So 1x, all right, so in the original function, 1x ranges from -3 to +3. The y value ranges from 9410 and back to 149, right? Okay, so now let's consider this new function here. If we subtract 1 to the x in the original function. Okay, in order to keep the y unchanged, this time the x must be enlarged by 1, right? So if the original value is -3, so in order to keep the y still be 9, so x value in the new function must be 1 unit larger, right? Which becomes -2. And -2 here becomes -1 in the new function, right? And following the same logic, each value here in the original function becomes 1 unit larger in the new function. That is equivalent to move the original function right by 1 unit, right? Can you follow me? Okay, so in a summary, based on the graph of y equals x to the power of n, the parameter d corresponds to a horizontal translation to the left if d is less than 0, or right if d is greater than 0. Okay, for another example, if the original function is y equals x squared and the new function is y equals, we add a 1 to the x here, right? So following the same logic, for the same value of y, if the original value of x is -3, in order to keep the y unchanged, x should become 1 unit lesser, right? So -1 becomes -4, -2 becomes -3, -1 becomes -2, etc., right? So that is equivalent to move the original function to the left by 1 unit, right? Because as you can see here, each point of x here has been shifted 1 unit left. Understand? So the whole graph would be shifted 1 unit left. Okay, so if we draw a graph to illustrate this question, this is our original function, y equals x squared, right? And if we subtract 1 unit to the x, this means we need to translate the original graph by to the right by 1 unit. So this is the square of x minus 1, right? And if we add 1 unit to the x in the original function, this is equivalent to translate the original graph to the left by 1 unit, right? So this is the square of x plus 1. Understand? And accordingly, the vertex here in the original function is also moved correspondingly, right? Okay, any questions? No? All right, let's do some practice. So how do you obtain the graph of y equals the square of x minus 2 from the graph of the function y equals x squared? Okay, I'll give you 2 minutes to think about it. Okay, have you finished? Okay, note here, we subtract 2 units from the x in the original function, right? So this parameter here corresponds to a horizontal translation. So we can just simply horizontally translate the graph of the original function x equals x squared, right? To right or left. You can think of it like this, right? In order to keep the y unchanged, each x should be enlarged by 2 units, right? That means the function should be moved to the right, right? So we should translate the graph to the right by 2 units. Okay, so if you draw a graph to illustrate this problem, this is all original function, right? X squared. And if we put a minus 2 here, this means we need to translate this function horizontally by 2 units to the right, which becomes the blue curve here. This is the square of the difference between x and 2, right? Okay, please have a look at this. Do you have any questions? No? Okay, so let's make a summary. Actually, we can just combine all the translations we have learned in this statement. So suppose we have a original function y equals x to the nth, right? And the new function look like this. There are 4 parameters, right? First parameter is a here, which enlarges the whole function by a factor of a. And second parameter is k, which is in front of the variable x. Third parameter is d. Third parameter is c here, which corresponds to a translation vertically, right? And the last parameter here is d, which corresponds to a translation horizontally. So the conclusion is actually we can do all the translations one by one, right? So based on the discussion from this should be 1.1 to 1.4, we can see that graph of the function of the form y equals a times k times the difference of between x and d and raised to the power of n plus c, a and k are not zero, can be sketched by applying transformations to the graph of the function y equals x raised to the power of n, right? And please note the transformation represented by a and k must be applied before the translation represented by c and d. Whereas the parameter a corresponds to a vertical stretch or compression. And if a is negative, a reflection in the x-axis. And parameter k corresponds to a horizontal stretch or compression. If k is negative, a reflection in the y-axis. And parameter c corresponds to a vertical translation up or down. This is the simplest, right? And the parameter d corresponds to a horizontal translation to the left or right. Okay. All right. So following this, let's see an example. So suppose the graph of y equals x to the 4th is transformed to obtain the graph of the new function here. State the parameters and describe the corresponding transformations. State the domain and range, the vertex, and the equation of the axis of symmetry, and sketch a graph of the new function. Okay, so let's answer these questions one by one. First, state parameters that is correspond to the transformation. So there are 4 parameters, right? What is your a? K, c, and d, right? And how these parameters corresponds to our transformation. So this is our a, right? So a is 4, and this is k. K is 3. And here is our parameter c, right? Plus, remember that in our previous statement, the parameter is plus c. So as you can see here, it's just plus minus 6. So c is minus 6, right? So here, the statement says x minus d. So the parameter here is x minus minus 2, right? Because positive 2 is minus minus 2. So a parameter d is minus 2, right? These are all the 4 parameters that will be used in the transformation. Okay, so what does the transformation look like? The transformation should be based on the original graph First, we need to vertically stretch the original graph by a factor of 4, right? And then horizontally compress, because k is 3 here. That means horizontally compressed by a factor of 1/3, right? And then because c is -6, we need to vertically translate the graph down by 6 units. And then because d is -2, that means we need to horizontally translate the original graph to the left by 2 units, right? Can you follow me? Okay, state domain and range. The domain is, of course, entire set of R, right? How about the range? So note here, we have something to the power of 4. Something to the power of 4, there is a minimum value, right? The minimum value is 0. So the minimum value of y is 0 minus 6. So y can also be any value that is above -6, inclusive, right? So this is our range. The vertex. Okay, in order to get a new vertex, we need to study its graph, right? So this graph is simply transformed from the original graph of x to the 4th. The graph of x to the 4th will look like this, right? So this is our vertex. So after transformation, the vertex has also been transformed to a new position following this transformation, right? So one of the methods to find the vertex is just to use the following transformation, right? And another way to find the vertex is note that the vertex of x to the 4th is just a minimum point of this graph, right? So we have already know that the new graph, for the new graph, the minimum point is when x equals -2, right? Which makes the first part become 0. So the vertex must be when x equals -2. So when x equals -2, y equals -6. So this is just the vertex of the new function, right? And the equation of the axis of symmetry. Okay, also note that the equation of the axis of symmetry of the original graph is just x equals to the x coordinate of the vertex, right? For example, the equation of the axis of symmetry in the original graph is just x equals 0. And we have already know that the new graph, for the new graph, the x-axis of the vertex, the x-axis, the x coordinate of the coordinates of the vertex is -2, right? So the equation of the axis of symmetry must be x equals -2, right? Can you follow me? Okay, last, sketch a graph of the new function. All right. How do we sketch a graph of the new function? Okay, usually we'll find its x-intercept, y-intercept, and the vertex, right? So we have already know that the vertex is -2, -6. So what is x-intercept? X-intercept is just a value that makes the whole function 0, right? So let the function here be 0. And then we can solve the value of x, right? Which is and then cancel a 3. Or not a 3. Should be okay, which means all right, which means x plus 2 is positive or negative the fourth root of times 1/3, right? So this means x equals -2 okay, and then you can calculate this using your calculator. This is just the x-intercept of the new function. So how about the y-intercept? Y-intercept is simply let x be 0 and find the corresponding y, right? And if x is 0, we know that y is 4 times 3 times 2 to the 4th minus 6. This is 5178, right? Okay, so if we use all of the information, we can draw the graph of the new function like this. This is a vertex, right? -2, -6. And then you can label the x-axis, x-intercepts here and y-intercept here, right? Y-intercept is 0, 5, 1, 7, 8. Okay, I'm not gonna calculate the x-intercept here. You can calculate them by yourself after the class. Okay. All right. Any questions? Okay, so now it's your turn. This time you need to answer all of these questions by yourself. Okay, I'll give you 3 minutes to think about it. All right, have you finished? Okay, let's have a look at the solutions together. Okay, first of all, what are the parameters? So this is our A, right? A is 1/4, and this is our K. K is -2, and C is +2, and D is 1, right? So the corresponding transformations are based on the graph of the original graph. Based on the graph of the original function, apply the transformations in the following order. So if A is 1/4, that means first we need to vertically compress by a factor of 1/4, right? Next, K is -2. So we need to horizontally compress the original graph by a factor of 1/2. Note that there is a minus sign, right? So then we need to reflect it in y-axis. Understand? And the third, because D is -1. -1 means horizontally translate the original graph to the right by 1 unit. And last, C is +2, which means vertically translate up by 2 units. Okay, so pay attention to the statements here. When you do your exams, you need to exactly express the transformations one by one. Okay, and remember, you need to do the translations corresponding to A and K first, and then C and D. Okay. All right. So the domain of the translated function is apparently -infinity to +infinity. There is no constraints to the x here. The range is 2 to infinity. Why? Because for the first part, the smallest value of the first part is 0, right? So something raised to the power 4 is always a non-negative number, which is equal to or greater than 0. So the first part, the minimum value of the first part is 0. So y cannot be any value that's below 2, right? So the range of y is 2 to +infinity. Okay, next, the vertex. So this time we can use the first method to calculate the vertex. So the original graph looked like this, right? And if you want to find the new vertex, you can simply just apply the transformations to the original function, also to the vertex, right? But note that the vertical compression and horizontal compression has no effect to the vertex. Why? Because as you can see here, no matter how you compress the function. So let's see here. When you compress or stretch the function, there is no effect to the vertex, right? Only horizontal or vertical translation has impacts on the vertex. So the first two transformations has no influence on the vertex. The third translation has impact on the vertex. Third translation states that the curve should be horizontally translated to the right by 1 unit. So if the original vertex is 0, 0, after translation, the vertex becomes 1, 0, right? And the fourth translation, which states vertically translate up, also has impact to the vertex. This means the vertex is also translated up by 2 units. So the point becomes 1, 2, right? So this is all new vertex, right? And we also know that the equation of axis of symmetry is x equals to the x coordinate of the vertex. So the equation of the axis of symmetry is just x equals 1, right? And if you graph this function, it will look like this. So first of all, this function cannot be any number that below 0, right? So this number must be like this. There is no x-intercept because this number is greater than or equal to 0, and plus 2 must be equal to or greater than 2, right? So there is no x-intercept. And we also know that the vertex is 1, 2. So label the vertex here, 1, 2. And then it's better to also mark the y-intercept, which is when x is 0, the value of y, right? So when x is 0, y equals 1/4 times, which is sorry, made a mistake here. So when x is 0, y is 6, right? So the y-intercept is 0, 6. And a sketch of the graph of the new function would look like this. Okay, any questions? No? All right, let's have a look at the second part of today's lesson, transformation of any given function. Okay, so actually the statement in 1.5 can also be generalized to other functions, y equals fx. This is more general, right? It could be any function. The graph of the function of the form y equals a times f k times the difference of x and d plus c, where a is not 0, k is not 0. Remember that the 4 parameters are a, k, c, d, right? And then the new function can be sketched by applying transformations to the graph of the original function y equals fx. Okay, also note that the transformation represented by a and k must be applied before the transformation represented by c and d, where a corresponds to a vertical stretch or compression. And if a is less than 0, a reflection in the x-axis. K corresponds to a horizontal stretch or compression, and if k is less than 0, a reflection in the y-axis. C corresponds to a vertical translation up and down, okay? Because C applies to the whole function, right? D corresponds to a horizontal translation to the left or right. Okay, I hope you understand this conclusion. So let's make a practice to illustrate how this statement is applied to function transformation. Okay, so this time our function becomes y equals sine x. This is a trigonometric function, not the function that we have learned in the previous 2 lessons, right? So this function is more general. So this time it is a trigonometric function, and we know that this function has the following graph. Okay, if you don't know the graph of y equals sine x, it's okay for this question. It just tells you that the graph of this function look like this. Question is, state how to get the graph of the function y equals sine 2x plus 1 from the original function y equals sine x, and then sketch both y equals sine x and y equals sine 2x plus 1 on the same xy plane. Okay, I'll give you 2 minutes to think about the question using the statement here. Okay. All right, have you finished? So how do we do the transformation? This is our original function, right? Which is fx equals sine x. This is a new function. The new function is obtained from the original function, right? So here, actually the transformation is just from fx equals sine x to f2x plus 1, right? Why? Because fx is sine x, then f2x plus 1 is just sine 2x plus 1, which is here, right? So the transformation is from fx to f2x plus 1, right? So what are the parameters? So there is no parameter a, right? Or in other words, parameter a is 1. There is no effect to vertical stretch or compression, right? So k here is 2. This means we need to do a horizontal compression or stretch, right? And there is no d here. So we don't need to do any horizontal translation. And there does have a c here, c equals 1. That means we need to translate the whole function up by 1 unit, right? So there are 2 transformations. First of all, we need to compress the function by a factor of 1/2, right? Because k is 2 here. And after that, we need to shift the whole function up by 1 unit. Do you understand? Okay, so this is a nicer way to write the whole solution. Okay, as we have discussed, if we let fx equals sine x, then f2x plus 1 equals sine x plus 1, right? So the transformation is from y equals fx to y equals fx plus 1. The two parameters are k equals 2 and d equals 1. So transformation parameters are k being 2, c being 1, based on the graph of y equals sine x. Apply transformation in the following order to get the graph of the new function. First, horizontally compress by a factor of 1/2, and then second, vertically translate up by 1 unit. And then if you draw the two graphs on the same xy plane, the two curves should look like this. The red curve here is the original one, right? So following the transformation, first compress by a factor of 1/2, and then translate up by 1 unit. The blue curve here is a graph of the new function, right? Okay, any questions? Okay, if you don't, let's make a summary of today's lesson. Okay, let's revisit today's learning goals. Now, after today's lesson, now you should be able to determine if a function is a general power function or can be obtained by transforming a general power function. For example, this is a general power function, right? Sorry, fx equals x to the fourth. And then if I give you a new function, for example, this one, you should be able to determine that this function can be obtained by transforming the general function, the general power function here, right? Okay. Second, you should be able to know how to apply transformations from the original function y equals x to the power of n to a new function with the form here, right? And more generally, from any given function y equals fx to a new function with the form like this, right? The four parameters are a, k, c, d. You should be able to know how they correspond to the transformations. Okay, last, you should be able to sketch graphs of functions with the form y equals a times k times the difference between x and d raised to the power of n plus c, and analyze their key features, including domain, range, parity, monotonicity, and behavior, asymptote, etc. All right? Okay, so this is the end of today's class. The rest of the time is reserved for you to complete today's homework, okay?